Before we going to the example, let me start. This subject combine the mechanics with the material. What the mechanics you study is the engineering statistics, okay? And that mean what? That mean in the mechanics you be able to draw the free body diagram. I said able to, okay? That means you got to do it correctly. And then you use the equation of equilibrium to analyze it. And the result is what? The result is when the structure subjected to external load, okay, that may be concentrated load or uniformly distributed load. You use this 1 and 2, you can determine the reactions, okay, and then you also can determine the internal forces and moment. That's called mechanics. Now you move a little bit further. It's the mechanics of material. What kind of material in engineering? You may say it's maybe the structural steel. Okay, structural steel is maybe cast iron. You may see the cast iron in the railway. Thailand is building the high-speed train. Okay, the railway of the train made by cast iron. The structural steel, a lot of things made by it. Maybe the car, maybe the building, okay, maybe the factory. A lot of things made by structural steel. Means maybe concrete, okay. It's also maybe the aluminum. Aluminum used a lot in the what? In the airplane, okay, and it's also used in some building. There's a lot of things, including the recent development on the fiber reinforces plastic, okay, and that means the material going to involve a lot of things, but most of the material is the deformable material. That means when it's subjected to the force, it will deform, such as if you have the rubber band, when you pull it, the rubber band will deform, okay. This kind of material is so-called the deformable body. However, in the analysis and design of material, we talking about the strength, okay, to be the beam, okay, under the application of the force. This beam must be strong enough to resist 100 kilonewton force. That means it has enough strength. What is going to control it? The stress. That's due to the internal force and moment. The maximum one occur over here must be less than or equal to sigma allowable, which is going to be equal to the property of the material divided by factor of safety, okay. And then under this force, the beam also must be bent, okay, and the beam cannot bend much, such as this one. When you bend it, okay, you can see it, because the beam usually have the wall under it. If it has large deformation, it will push the wall and the wall will crack, and that's going to make your building ugly, okay. And that means what? That means you got to measure what? Measure the deflection that occur during the force, and you said this one must have enough stiffness, okay. The Vmax that occur over here, that is Vmax, gonna be less than or equal to allowable deflection is going to govern by such as the length. If you measure this, it's going to be the length, and then divided by 240 if there is not a wall undercut. So this is a kind of combination of your own knowledge, two of them. This come from engineering static, and this come from engineering material. Due to the combination we have discussed. Any question for this first discussion? No one? Okay. Then coming into our problem. I took you to Dornberg International Airport. Okay. At the airport there is airplane. Okay, this is a Nokia. And then the airplane has this vehicle to pull it or push it out of the parking hole over here. Okay. Again, the airplane can do it by itself. Yes, the airplane can do it itself, but most of the time we have this vehicle. And let us just consider this small yellow structural member. Okay, is at the hole over here, is at the hole over here. That represent the tow bar. One link to the landing gear. Another one link to the vehicle. When you put this one into the vehicle, you can say this is the member. Okay, this member connect to the vehicle. Okay, and by that connection, they use the bolt. The bolt gonna be something like this one. Okay, push into that one, and then let me make some discussion. When you going to move this one forward, that means you're going to drive your car in this direction, and then this member is going to be in tension. Okay, it's going to be in tension. And if in the reverse direction you concentrate it in this direction, that means the member is going to be in compression. In the first chapter, we're going to consider this member. In the previous course, we know that this called the two-force member. In this course, we may call it axially loaded member. Okay, when it's pulled, the airplane is going to be in tension. This one in tension, and then you may say it's T, and then you parenthesis. And another one, this one is in compression. Okay, and if you cut this structural member and you consider it, actually the material in the member will resist the force by developing the stress. Okay, and if the force that you use to pull the airplane is, let's say, it's going to be P, and then your structural member over here, okay, it may has the rectangular section. Okay, it's maybe 50 millimeter by 50 millimeter. So the cross-sectional area of this member is going to be 2,500 millimeter square. If you divide the P by the A, you compute this one. We call this one as the normal stress. Okay, and we call this symbol as the sigma. So sigma equal to force. This is going to be the force divided by the cross-sectional area. And then if this force is going to be 10 kilonewton, so this one going to produce the stress over 10,000 Newton divided by 2,500 millimeter square. Then you get it to be 4 Newton per millimeter square. Or if you use 1 meter is 1,000 millimeter, so 1 meter square is going to be 10 power 6 millimeter square. So by doing this, okay, you may say this can be changed to 4. This is going to be converted by this one and time 10 power 6 Newton per meter square. We call this to be 4 megapascal. Okay, so in short, 1 megapascal is going to be 10 power 6 Newton per square meter, and it's going to be 1 Newton per meter square. I will give you the first start like this. Okay, and then there is 2 things. This problem, you determine the stress. Okay, even stress. We call this problem as the analysis. Okay, this is the first type of problem to determine the stress. Another method. Okay, we also call it as the design. Okay, in the design, we're going to determine the area. So in the design, we just change the form of this equation to this one in order to determine the size, the dimension of this tow bar. Okay. However, in this design, the sigma that you use will be, this one will be given. Okay. If it's not given, you also be known by testing it. As I told you, we have this equation. This is sigma allowable. This one you can test it in the lab. Okay. This one is set by the design code. Okay. That's maybe from the Engineering Institute of Thailand, WSOT. Okay, given by official. So this is from the lab. In the problem, Ajahn will give you, okay, sigma allowable. If I not give you sigma allowable, I will give you sigma supply and factor of safety. This one called factor of safety. Okay, and then by doing this, we just determine it, and I will do the calculation for this later. You will get the size of this. Now we come to the next important thing is the connection. Okay, in this connection is a kind of a thing. For example, you have the tow bar like this, and then you pull it. Okay, you pull it, and then you see my pen. My pen is over here. This my pen connect, okay, to the car, and then this tow bar like a paper band over here. Show you over here. Okay, by doing this, you may draw this one as the tow bar subjected to the force, and this tow bar connect to the part of the vehicle. Okay, and then it's supposed to be bigger than this. Then it also have the force occur over here, right, to resist the pulling force. And it says this pulling force is 10 kilonewton. That means it's going to produce the 10 kilonewton, the same thing as 10 kilonewton here. what happened is this one will connect by the ball. Again, where is the ball? This is the ball, okay, the ball. And then the ball is going to connect them together. Okay, that means what? The ball used to transfer the force, okay? How it's going to transfer? So by doing this, again, you gonna draw the toe bar. And then, no, this is not toe bar. This is the link over here, the link to the car. And you also gonna draw the toe bar. Let's say this is the toe bar. This is 10 kilonewton. And also this one is 10 kilonewton. And between it, there is the ball that I show you over here. The ball is going to be over here. What happened is during the application of 10 kilonewton, there must be 10 kilonewton force occur at the hole here. And also there must be another 10 kilonewton occur over here. Okay, this 10 kilonewton occur the force here, and this 10 kilonewton produce the force here. And what we have is this one will subjected to the force, one to the right, one to the left. Okay, and then there is somewhere in between is a press over here. Since the plate is really thin, the eccentric length over here that's produce the moment, this is approximately 0 in this case. And then what we have is we just consider, let's see, we consider the top portion, I cut it over here. And then the force occur over here is going to be this one. And this one is the force that's parallel to the surface. When you trying to pull, this is two-way, okay? You see the red, okay? One is going to move here, one is going to move here. That is going to produce this one. We call this one as the shear force. So the connection between toe bar over here, okay, and the landing gear and toe bar to the vehicle. This is to the landing gear, and this is toe bar to the vehicle. Is the hinge. This is a hinge, and the hinge is subjected to the shear force. This is the mechanics that I show you. That's due to this one axially. This show you only one shear, okay? Over here. This called single shear. And there is another thing. If you trying to connect in the other way, if you connect these two things, if something like this, the ball is in single shear. But in some cases, we connect the plate in the form something like this. This is going to be so tough. Something like this. There is one plate, 10 kilonewton, and there is two plates in this side. It's going to take 5. And then you can see, there is going to be two cut. Okay, by doing this kind of thing, we're going to call this one as the double shear. Okay, and then the shear force, we may call it V. V is going to be V over A. Okay, and this one E, V is going to be 10 kilonewton, the same thing as before. And let's say this is the area. Let me assume it to be 100 millimeter square. Okay, by doing this one will be cut, and it's going to be 100 Newton per millimeter square. This is going to produce the shear stress of 100 megapascal. Okay. Let me use this example to persuade you to trying to study, to think. One is the normal stress, okay, and this one is going to be what's so called shear stress, okay, and if you not touch it, that is going to be your problem. You got to find some real world in order you guys will understand it, okay, and Ajahn only be the guide that's trying to persuade you to understand this thing. Next, we come to the stress. The definition of it, okay, that is the real thing we're talking. The definition of stress is indicate the intensity of the internal forces. Like I told you, okay, if you consider this axial force member and this one subjected to the compression, the compressive force will be applied to the centroid of this member, and it will produce the compressive force. Okay, if this compressive force is P, you may use the summation of F sub y equal to 0. You can find this one to be P. But this P is not real. Okay, it's not real. It's just a way to compute the stress. In actuality, what occur over here is going to be the stress that occur on every material point on the specific surface. Okay, and then the definition of this one, the stress, is the force, is intensity, the force divided by the area. Okay, and this called normal stress. The symbol is sigma. By doing this, we call sigma equal to limit of delta F by delta A when A approach 0. Is mathematics definition. Okay, in engineering definition, due to this kind of forces, the stress will be uniformly distributed. Okay, that means everywhere, every material point on this section has uniform stress. So by doing that, you can take limit out of this equation. So it's going to be the force divided by the area. Okay, and then we come to the next one. The next one, you may use this sponge. Okay, and then when you apply the force, your force like this one. Okay, that means the force in parallel to the surface over here. Unlike this one, the force is perpendicular to the surface. Okay, that's why we call this one normal stress. When we talking about the shear stress is due to the internal force, internal shear force parallel to the section. Okay, and then the area that's used to compute the shear stress is going to be this area. Okay, you got to understand this. And then this one going to call the direct shear. The symbol is tau. Okay, this may call direct shear stress. Is going to have many shear stress, one for the torsion, one for the transverse shear. But this one is the simplest shear. We call it direct shear. Okay, and then for the definition that I just said, since the force applied passing to the centroid of the section, okay, and when the force passing to the centroid of the section. Also, the material of the member is homogeneous. Homogeneous is mean all the material that's be here, they are the same, such as if they are the steel. Over here, all of the material point is the steel. Homo is mean the same. Okay, and then it's also isotopic. Isotopic is mean if the material, okay, you test it in this direction and have this property, is going to be the same as this one. That means the material have the same property in every direction. Okay, this one may be the aluminum or also maybe the steel. Okay, this one has the cross section of A, subjected to the axial force passing to the centroid of the section, and then the equation is like this. And there is two types of them. One is tension, another one is incompression. For incompression, is only for the short member. Okay, why I translate that? Because if it's going to be in tension, okay, you cook it, it's going to be elongated. But in compression, if this one is too slender, when you compress it, it's going to buckle like this. Okay, but we are going to consider the one that is short. Okay, if the one is short, there is no buckle. The long member, for the long member, we will long compression member, we will study it in chapter 13. So wait until there. So right now, only short compression member is considered by using this equation. Okay, the unit may be 10 power 6 Newton per square meter or megapascal is equal to Newton per square meter. Beware about unit also. Okay, there is a lot of number of axially loaded member, such as this one for the truss. Okay, you study this one already. The force that's applied to the truss is applied to the joints. Okay, under this kind of force, for sure, this part going to be in tension and the top part going to be in compression. There's the members. The members are two force member. If you remember from the static, and in the two force member in this subject, we may call it axially loaded structural member. The same thing over here. The force from the floor transfer to the floor beam, transfer to the sinker, transfer to the floor beam, and act to the truss like this. By doing this, this one gonna be in tension and the top gonna be in compression. Okay, and then coming to the machine like this. If you have the weight here, you're talking about this member. Okay, the weight going to trying to rotate about this point, and the force here is going to rotate in this direction. That's why you know the direction of the force in this hydraulic cylinder. Okay, this may be the model in the real thing. In the real thing, we also have this for the truss, roof truss, this for the bridge truss in our university, this for the machine. The part of the machine that we consider is the hydraulic cylinder. Okay, it is two forces member. Okay, and then there is going to be the force that produce the normal stress. Okay, is going to be the force P divided by A. Every member that I just mentioned. But when we talking about the joint, this is going to be the connection that Ajahn just tell you from the tow bars. This is going to be the hydraulic cylinder. This is hydraulic cylinder, and there is going to be the steel rod. Okay, the same one that I show you is going to be something like this, Oop. Like this. Oh, that's going to be hard, a little bit hard to show you. Okay, to be something like this. It's going to have the bow sometime, and it's just be this. And by doing this, you may see if this one may be forces applied to the pin. Okay, the pin is going to be over here. This is called pin connection, and we usually call this one as the pin. Okay, let me illustrate this a little bit. I know it's too much. And then by the application of this force P, what occurs is the plate over here will produce the reaction to resistance. Okay, or in short, if you like to make this one simple, you may take this pin out. Okay, and then this one subject to the force P, and then the plate over here will resist it. Okay, if the eccentric length is very small, we assuming, okay, moment due to this kind of eccentricity is approximately 0. By doing this, okay, you may say this portion will be cut. The cut point is over here. Okay, the cut point is over here. And if again you draw the free body diagram, only the cutting portion over here, that means you have the force P over here. Again, it's going to produce you the shear force, okay, on the left and on the right. This one we call it double shear, okay, double shear. And this one going to be V, this one going to be V by summation of f sub y equal to 0 to V equal to P. So V equal to P over 2. By doing this, we will have tau equal to V over A. And then you have this one, tau going to be P over 2A. That's going to be the shear stress in the double shear format, which is different from this one. Okay, this one, which one? This one. This is going to be the single. Actually, it's going to be single shear stress, but this one going to be double shear stress. Both of them are used in many kind of structure and machine. Okay, and then there is column. Let's say this is column. This is two-story column. This column connect by the beam over here. Okay, the beam over here will develop the force over here. Let's say this is going to be the point A, and the force over here will be P sub A. And then you have this column, right? Okay, this column link to the point B. This is going to be the point B. And again, the point B connect by the force and the beam is going to be produce the force P sub B. Okay, apply over here as point B to be P sub B. What happened is the column on this portion and the column on this portion, they are different size. You may model it with the larger column. Okay, anyway, it's under the axially compressive load. That means what? That means they're going to the column going subject to the load that's applied to this line and passing to this point. We call this point C. Okay, we call this point let's see the centroid of the section. Okay, so the force align to each other from the top to the bottom. So we may model this column, the real one, okay, in this one. If we interested to determine the maximum average normal stress occur on this column A, B, C, we got to consider this column into two parts. One for the AB, one for the AB, another one for the BC. By doing that, we're going to use the free body diagram. And then we're going to use the equation of equilibrium to what? Equilibrium to determine the internal force in this portion AB and this portion BC. And third, we determine the stress equal to internal force divided by A. Okay, this going to the step, and then we going to first we find the internal force. We cut this column in this one. Since the force is axially loaded, the force are equal no matter you cut it anywhere. They are constant. Okay, and this is going to be P sub A. You use the equation of equilibrium to determine it. And then you cut another one over here. Now you can determine the internal axial force in this portion to be P sub A plus P sub B. Okay, and then if its tension usually is put in positive. If it's in compression, it's going to put in negative. So this one going to be in compression, and this one also going to be in compression. Okay, and then you just distribute the stress easily, and then you may just compare it. So this is the column that's different from the tow bar. Okay, the tow bar can be in compression or in tension when you pull or push the airplane. But most of the time, this column, they are in compression. Now, we move to a simple example. Sometimes the tow bar or maybe this kind of load may be subjected to a more complicated load. So let's say this is going to occur due to the cable 12 kilonewton. This is 22 kilonewton, and in between, if you like to check, you use the summation of x sub x equal to 0, and let's say this direction is positive, so you have minus 12, and you have minus this one 18, and you have this one plus 8, and then you have this one plus 22. This is 0, so it is correct. Okay, it is in equilibrium. Okay, in equilibrium. If you check summation of f sub y equal to 0, they didn't consider the weight of this, so it's automatically correct. And due to the force applied passing to the centroid of the section, and also the length over here, they are equal. Okay, if you take summation of the moment equal to 0, this one going to be in equilibrium. Okay, now we like to determine the maximum average normal stress. Okay, for this member. This member has 10 millimeter thick. That means it's going to be in dimension. It's going to have the square section with this one for 10 millimeter. From this one going to be 35 millimeter. Okay, that is for the steel bar. Then, if you like to determine the normal stress, okay, from the equation you're going to be determine the internal force P. Okay, now you know only A. The A is going to be 10 times 35. That is going to be 350 millimeter square. So this one already known. Okay, so the P, you got to calculate by using the free body diagram. You cut this one. Okay, this is going to be P sub AB. AB is going to be the symbol, is the portion of the bar between point A and point B. Now, you're going to determine this one. This is for the BC, for the portion BC, and this one for the portion CD. Okay, you understand the third law of Newton, right? So this portion CD, you can cut it like this. Now, you do the summation of x sub x equal to 0. Okay, use the summation of x sub x equal to 0. You got P sub AB equal to this. Use the summation of x sub x equal to 0. And then put this direction to be positive. DC is going to be what? P sub BC is positive. It's going to be in this direction. It's going to be equal to 12 plus 18. That is going to be 30 kilonewton. Okay, you got this one, 30 kilonewton. And the last one, summation of x sub x equal to 0. Now, this direction is positive. Different from this one, P sub CD is going to be 22 kilonewton. And you can see this one is in tension. This one is in tension. This one also 22 kilonewton is also in tension. All of them are in tension. That means if you connect something like this, intention is going to be elongated. Okay, but by checking this, we only interest the stress. Since the area is equal, okay, and if you draw the shear force diagram, this portion is 12, this portion is 30, this portion is 22, and the equation just be sigma equal to P over 300 millimeter square. So the force P going to be given, okay, because of what? Because of P max will produce sigma max. So we know the sigma max will occur in this portion BC, and then we can compute the maximum average normal stress easily. Just divide this one by this one, or actually if you prefer, you just take this one out and divide this one by 350 millimeter square. Newton per millimeter square is already megapascal. Doing something like this is better. Okay, it's 30,000 divided by 350. And then the stress occur on every material point is going to be the same. Okay, yeah, that means due to the axial load and the steel, which is the isotropic and homogeneous, the stress is going to be here. There is no force here. Okay, this is unreal. Okay, this is unreal. The real thing is here. Actually, this stress is due to the force 30 kilonewton like this. And then the problem maybe get a little bit more complex. The previous example, in just one piece, subjected to different loadings. But this one, they have the weight that's hanged over here and said this one has 80 kilogram. That's going to be 80 times 9.81 to be in the Newton. And then the log AB, log AB is here. That has the diameter. We use D to be the symbol of this diameter, and this is 10 millimeter. Then we come to the BC. This is D sub BC is 8 equal to 8 millimeter. BC is smaller. Okay, AB is larger. Anyway, the stress is equal to internal force divided by area. Not only the A is important, the P also play the role to determine the maximum average normal stress in the lot. Okay, for sure they should not be equal. But how we going to do it? We're going to go back to engineering statics when we consider equilibrium of particle. Okay, by doing this, we consider the B as the particle. We will draw the free body diagram of this one. Then we use the equation of equilibrium. Okay, equilibrium. By doing this, find the internal forces in the lot. Draw the free body diagram. You just set up the X and Y axis. Okay, this is going to be the first step. Set up the X and Y axis, have the origin over here. Then draw this one, the known force. Then draw the unknown force, F sub BC and F sub BA. Then draw the angle 60 degree for this one. And this one ratio of 3, 4, 5. And based on the previous knowledge, we will use the equation of equilibrium. Before you can use the equation of equilibrium, you must, okay, separate this one and this one by using the parallelogram rule. Okay, that's one going to be F sub BC times what? This is in the horizontal direction. The ratio must be 4/5. And this one is going to be F sub BC. This is in vertical direction, 3/5. And also, if you come in this way, if you project it downward like this, this is going to be F sub BC. This angle, okay, in this direction is going to be cosine 60 degree. And then also in this one, you may project it in this direction. This one will be F sub BA. And then that's one going to be sine 60 degree. Now, the equilibrium can be in the horizontal direction. Okay, these two forces must be in equilibrium. And also another force in the vertical direction, they also must be in equilibrium. These two up, and it's going to be balanced or in equilibrium with 784.8. So depending on you going to use summation of x sub x equal to 0, then if you push this one in this direction to be positive, again basis upon this one, F sub BC times 4/5 is positive. F sub BC cosine 60 degree is going to be negative. So you cannot solve this equation yet. You can get the ratio between them. Now, you know this one, okay, if you put this one as the positive, this one F sub BC times 3/5, and this one upward, this one F sub BA sine 60 degree, two of them upward. So they are combined together. So these two combine together. And then you get the downward force of 784.8 is going to be negative. Solving these two equations, okay, you will get the internal forces in the rod BC and rod BA, but the area of the lots are different. So the normal stresses occur inside it will be different. Next, we divide. Sorry, I pushed my ball down. F sub BC 398.2, and since the lot mean circular section like this. Okay, the area of this circular one may be pi diameter square divided by 4, or you may use only pi radius square. It's up to you. Okay, this one is pi radius square. Okay, and then you get this one 7.86 megapascal is in tension. And F sub AB over here, even though it's bigger, diameter is 10 millimeter, you change it to radius, okay, in meter like this, you get this one 8.05. So the maximum stresses occur on the bigger lot, okay, in the lot AB. And then when you draw this one for the lot AB, okay, the forces will produce stresses everywhere in the material on the cross section of the lot, and they are distributed equally, since the force we consider is the axial force and the material is the steel, which is homogeneous and isotopic material. And if you bring the material point, you cut a small material point, okay, to consider, you may draw this one. This one we call it the stress element. Okay, we will draw a lot of this thing. This is stress element due to the axial stress, and if you more specific, is going to be tensile stress. There is a lot of nomenclature. Okay, that's maybe the same, and I like you guys to get used to with it. You're going to use it a lot. Okay, some of you guys may be further education in Australia or in United States of America. This kind of nomenclature, sigma, F, A, and the definition of the normal stress, those kind of things are general. Okay, next we come to the shear stress. Okay, and then coming into this one again. I didn't have much to show you here. Let me put my finger to be this portion, the bottom portion and the bottom portion. And then when you do something like this, it's going to be hard to demonstrate in this one. Okay, it's maybe something like this. And you imagine you put the force on the top. Okay, put the force on the top. This thing will be sheared. And then you may get the shear direction. This is theoretical, quite theoretical. Most of the time it's not like this, but it's just for demonstration. Okay, usually it's going to be easy if you use tofu. It's going to be easier than spong like this. Okay, and just push it like this, just demonstration that when you put it over here, okay, actually it's going to be something like this. But if for the small deformation, it's going to shear this spong as the one over there, okay, and over there. And what we have is we're going to consider this portion, okay, this portion, only consider this portion. You got to cut this portion and draw its free body diagram. Okay, you put this portion and then you just bring it down to this point. And then the surface on the left and on the right will produce the shear force, and due to this we call this one as the double shear. Okay, there's two V, and then if you do the summation of F sub y equal to 0, you will have what? You will have this one 2V equal to F. So the shear force is going to be half of the applied force F. Okay, and then typically by the assumption that we mentioned, okay, the material is isotopic, homogeneous, the deformation is very small, the stress is less than the yielding stress. We may assume the stress distribute over here. Okay, if this one is direct shear, we may say this is going to be the shear divided by A. So by doing this, the shear over here will be F divided by 2A for the double shear stress. Okay, it will be different from the single shear stress. Single shear stress, the V is equal to the applied force. And then this called the direct shear because the force produce the shear directly. There are three types of them: single shear, double shear, and pure shear. And what for the pure shear? Pure shear is not hard. For the pure shear, you may use the screw, and then you push, you take the screw, and then you stick it together, and then you poke it. Okay, by poking, you can see the slide of the paper slide on each other. That's going the shear force, and then it's depend on the size of the screw that you are connect. Okay, it's going to be the area of the screw that divide the force to produce the shear stress due to the pure shear. Okay, let me put the model. I just put this one and stick each other by using the screw like this. I pull this one, and if you dock it in the top view, and then another one you dock it over here. Okay, the force applied here passing through the centroid of the section. What I'm saying is going to be this screw area that's used to determine how equal to the force divided by this one. This one is the area of the screw. Okay, and this one, since this one has only one surface, this one is a kind of single pure shear. Okay, if you use another way, just put two screw. I supposed to take my blur out, take the background out. It's going to be easier. Okay, if this one like this, there are two over here. This one will be double pure shear. Okay, it's depend on the screw that you screw it. And by doing this, there is a lot of things about this. This is going to be single bow connection. Let me put this one. Where is my bow? Sorry, it's down here. It's down here. If you push this one like this, or this, okay, this one going to be single shear. Okay, and there are examples single shear over here. There are only two plates connect to each other by the bow. Okay, the eccentricity of the force is very small. Okay, very small, and then the force will cut the bow like this. Eccentricity over here is very small. Neglect the moment. Okay, so there is this portion that's shear. Okay, this is from the test. Okay, you can see this one, and then the shear stress is the force divided by the A. And then if you consider a lot of instruments allow you connect by the bow like that, such as this one. if you drive a motorcycle, your motorcycle will have this kind of instrument, and the link over here, okay, the link over here is in single shear when you use it. And if you just connect the screw, this also the single shear is single pure shear, okay, and it's going to be like this. And I already show you about this type of thing. There are 3 plates connect to each other. If one is on the top and the other is on the bottom, if the force over here is F, the force over here going to be half of the F. So the bow over here will subjected to half of the applied forces. I did draw the free body diagram to you guys already. So just go back to the previous PowerPoint and take a look at it. And then the F divided by 2A. So the stress in this form of construction on the bow going to be half, okay, of the single shear. And then for the double pure shear, you just screw it up like this, okay, and then do the same thing. Now, for the pure shear, there is only the shear that occur on the stress element, okay, on the top of it. Now, in conclusion, normal stress sigma equal to P over A, and direct shear, okay, is going to be tau equal to V over A. And you can see in really simple connection, we have the rod over here. We have the rod over here. This is maybe the steel rod, okay, and usually the steel rod must be in axial force passing through its centroid. And then over here is the bow. Over here is the bow. The bow is connect the rod, okay, with the U-joint over here. So the bow over here will subjected to the what? To the shear force. And since there is 2 cut over here, cut here and cut here, this bow is in double shear. Okay, this bow also in double shear. And the same thing over here. This bow also in double shear. So if this force is going to be P, okay, the tau compute here going to P over 2A, because there is 1 cut, another cut is over here, double shear. This is 1 cut, this is 2nd cut. Okay, this is going to be the starting point of this one. And when you determine the stress, okay, the problem is going to be the analysis, okay. And then if you move this one A up and P over sigma allowable, this problem gonna be the design. The same thing occur on this one. It's going to be A equal to V over tau allowable. Okay, I will give you this one. If I not give you directly sigma allowable can be sigma sub y divided by factor of safety, the same as tau allowable is going to be tau sub y divided by factor of safety. This one called the yielding stress is come from the lab. Okay, this is yielding normal stress. This is yielding shear stress. Okay, I like you guys to get a new concept. Okay, over here, the design and the analysis, which are important for engineers. Okay, another example. This example combination. This is the combination of the using of these 2 equations. Okay. Anyway, it took me an hour already. Let me break for 5 minutes, so you guys can take the water. Me too, and we will start the lecture again. Okay. 5 more minutes. I will come back. Okay, can you see my example? Anyone? Kenley? Malik?
Yes, I can.
Okay, we start a little bit basic one. Actually, the examination will be more complex than this. If you guys just has a paper and then you may do some demonstration on this problem easily. You can see my red, no, not in the same thing, something, going to be something. My red pen is going to be the 10 millimeter lot. It's going to be the same as this 10 millimeter lot. What happened is when I pulling this down, move it down, okay, what usually I should supposed to have a bigger one like this. What happened is this one will be in tension. Okay, the 5 kilonewton will produce the stress occur over here. That is going to be 5 kilonewton divided by A. Okay, this one, when you pull it, let me use my finger, and then this one will be something like this. But the portion over here, which is going to be the wood portion, as I show you, they may has the cut. Okay, let me show you by doing this one. There may be the cut, and the cut may be something like this. See, there is the cut that may occur on this side and on this side, and this portion will be tear out. Again, it's different from the picture. Real thing and theory is different usually, but by drawing this portion at the cutting over here, this is going to be the smallest compared to the real thing. That's going to be longer. It's not in a straight line because there are a lot of factors. But engineering, we just simplified it, make it a little bit easier. So what happened is this portion will subjected to stress. Okay, if we know the size of this total area, we just divide the 5,000 Newton by the area there. Okay, do we know the area of this? We know this one is 20 millimeter, but we don't know this one yet. Okay, if we assume this one to be 40 millimeter, so the stress that's occur in this portion will be 5,000 Newton divided by 40 and times 20 millimeter square. Okay, if this one is 40 and this one is 20 millimeter, but the problem didn't interested in the stress that occur in the wood, in the area of wood. They didn't ask us here. They asked us the other thing. I just expand the example. They asked us about the shear stress. One is going to be the stress. Let me put another one. The stress and occur on this portion. Okay, and other one is going to be the stress and occur along the line over here. They are different. This shear stress occur on the lot, and the shear stress occur on the wood. Okay, we find the internal forces. We separate. Okay, this portion, we take this portion, this piece. We take this one out. We just draw this one by taking this one. Okay, this one, and then we take this portion out. Okay, we take this portion out. and then we take this red right, and then we take this red portion, and then there is two surface that taking care of the 5 kilonewton. If you draw this portion again, this is 5 kilonewton passing to the centroid of the section, and then this one will be balanced by the force over here. Okay, summation of F sub y equal to 0. The force over here F, okay, F is going to be upward, is going to be 5 kilonewton, and F here by the third law of Newton, okay, is going to apply to this lot also. Okay, when we consider the lot, this force will apply to the lot. But anyway, when it push like this into dimension, it will cut, okay, this line and cut another line over here into dimension. So into dimension, if you draw this one will be something like this and subjected to the force over here of 5 kilonewton, and then it will produce the shear force V and V over here. If you do the summation of F sub y equal to 0, 2V, that one is positive, it's going to be 5, so V is going to be 2.5 kilonewton. Okay, and then this is going to be double shear, and then it's going to be 5 kilonewton for the lot. If you extend this lot a little bit like this, you may see this lot will subjected to the shear over here, the shear V over here. So this is 5 kilonewton by summation of F sub y equal to 0. V will equal to 5 kilonewton. This is going to be single shear. Okay, and then by doing this one, you use the internal force and then divided area. The single shear will be occur on actually supposed to be on this area. It's going to be A equal to pi r radius square, or you may be pi diameter square over 4. It's depending on which one you like. But for this one, the area will be this dark and red area. That is going to be this one, 20 millimeter, and then this one going to be 40 millimeter. So the area is going to be 800 square millimeter. Okay, this is going to be 800 square millimeter if you prefer. Now, for the start, it's going to be pi r square. It's depend on you guys. You may just use this one to be just 5 millimeter square. Okay, by putting, you will get this one directly because Mech Pascal is going to be Newton per square millimeter. Is going to be simpler to use the radius in the millimeter unit. The textbook is no good sometimes. I don't like it also. Okay, and for this one, the area here is going to be 20 times 40 millimeter. And the shear force here is half of 5 kilonewton. So it's going to be 2,500 Newton divided by, if I were you, just put this one 40 millimeter, this one 20 millimeter. Thing going to be easier because this is going to be in Newton per square millimeter and use this directly. Now, the shear stress in the steel rod is significantly larger than the stress in the wood. Okay, they just like us to think Why? The stress here is large and the shear stress here is small. Okay, usually steel has a higher strength. Okay, both in tension, compression, or shear, the higher strength than wood. Okay, usually when we measure this, we use the sigma sub y to represent the normal stress, the strength for the tension or compression of the steel. We use the tau sub y to represent it. Usually, tau sub y for the steel is going to be 120 megapascal. But tau, okay, is the strength of the wood. I just call it tau sub PL. That why is come from yielding. Let me put it over here first. PL is come from proportional limit. That is a terminology definition something, okay, of the material property of the wood. And this is usually just 10 megapascal, or sometimes it's only 5 megapascal, depending on type of wood. Some may be tech, some may be parawood, different. It depends on the type of wood. But why? Because usually steel has the higher strength than the wood. When you compute the stresses, both shear stress and normal stress that occur in steel, the number, I think, usually always larger than the one in the wood. Okay, for your information. And then type of homework. Okay, let us consider this one first before we go to the real problem. Okay, now we just talking about stress equal to P over A for the analysis, and A equal to P over sigma, and then tau equal to V over A, and then A equal to equal to V over tau. It's going to be analysis, it's going to be design. So the homework on examination is going to be analysis and design. Please do the homework. Do not just make yourself as the copy machine. Okay, if you like to see the work of your friend, study it before you like it into the homework. At least you will understand what your friend do his or her homework. So what type of problem? Okay, I said one is going to be the analysis. Another one is going to be the design. The design is going to find the size. Okay, so we come to the last one. This is going to be the design, because this asks you determine the diameter of the lot. Okay, that is going to be something like this, and the diameter of the pin at B and at C. This one is the design. Okay, and then another one. Let's talking about this one first. 1.8. Okay, this one asking you what? Asking you to determine the stress in the lot BC, and at the pin B, and the pin C. Okay, this one is going to be the analysis to determine the stress. Okay, this one going to be analysis, but I'm going to say this is going to be analysis 1. Another one is going to be analysis 2. The analysis 2, they're going to ask you the load that's applied to this structure. Ask to find the This one we know. We know W. This one also we know W. Okay, W is here. W is here. But for this one, W is going to be the unknown. I like you guys to understand this. There are going to be T types of problem in your work, in your examination. It's going to be one. Again, ask you directly to determine the stress. Okay. And another one is going to be ask you determine the size, okay, of the structural member. Another one, the last one, asking you to determine the load. So just guess what type of problem Ajahn will give you. This is the major thing. Okay, that's you guys to focus 3 types of them, how to work on it based on the equation that we have over here. So next, in the design, we're going to talking about the allowable. Okay, in the design, this one must be sigma allowable. This one must be tau allowable. And then the yielding stress and yielding shear stress. That means what? That means sigma allow is going to be sigma sub y divided by factor of safety. This one will be 125 megapascal. But for another one, this one is going to be tau allow, which is going to be yielding stress tau sub y divided by factor of safety. So this one is going to be 125 divided by 2. This is going to be 62.5 megapascal. Most of the time, tau allow is less than sigma allow. Okay, that is from the test. Okay, from the test in the lab. And then allowable. Why we do using the allowable stress in our design? Okay, the allowable stress is going to be the property of the material divided by something that's larger than 1, because there is some important thing. So first, the concept of the sigma allow. Okay, we use sigma allow to prevent the failure. Okay, in the big picture, still we consider sigma sub y as the failure stress of the material. Usually, sigma allow must be larger than sigma max. That's occur due to the external load. Okay, when the sigma allowable larger than the stress due to external load, the structure will be safe. Okay, and then the failure stress for the steel, we use the yield stress. For the concrete, we use the compressive strength. Why? In the concrete, most of the time concrete is in column, is in compression. We use the compression strength for the concrete. Okay, and this one is sector safety. Is set. This one set by authority such as Engineering Institute of Thailand. Okay, you may use that. Or in American, you may set by American Concrete Institute or American Institute of Steel Construction. Okay, but in this subject, okay, Ajahn will provide you with the factor of safety. It's maybe 2.0, it's maybe 2.5. Okay, and usually when you use the one set up by the EIT, usually they also set about 2. You'll be able to use 3 also. Which one is larger, you can use this. Okay, and the tau also in the form like this. And since the property of the material that we are considered is in the portion of linear, okay, and elastic. Okay, is linear proportion between the stress and the force. That means when we talking about the allowable stress, we may talking about the allowable force in the same form of equation. Just divide force as failure by the factor of safety. Okay, and then this one, this one is the mechanical property. Let us do the tension test. Very simple one. We use the material. We produce the material as the specimen. Okay, and then we going to test the specimen. Okay, it's going to be tested by using standard. Let me call it. There are a lot of standard. Okay, in America, you may follow the ASTM, American Society of Testing and Material. In Thailand, you may follow Thai Industrial Standard. In Japan, you may follow the Japanese Industrial Standard. There are standard in many countries. So you got to follow the standard because it's going to be the legal stuff. Okay, if you won't do it, you are going to be a bad guy. And by follow standard, when you pull it, okay, when the force is zero, the strain and the stress is zero. When you increase the force, you can compute stress, you can compute strain due to the elongation again and again. And then you just connect the point and you will get the graph. And we call this one as the stress-strain diagram. Okay, we will study this one in chapter 3. This is stress-strain diagram for the aluminum alloy. We have shape like this. But if you do the stress-strain diagram for the steel, it's going to be like this, like this. You study about this one already in the engineering material courses. Okay, and then there is a method that's determine the yielding stress of aluminum. We kept this one for 352. We use this one as the strength of aluminum. We're going to find sigma allowable of aluminum. That's going to be sigma sub ys over here divided by factor of safety. So in actuality, this one will be only half of this. Okay, in the design of steel, in design of aluminum, we use the yielding stress obtained from the test. Okay, and divide by factor of safety to get the allowable stress to make the structure safer from failure. Okay, and there are a number of reasons. What so-called safer? Safer for what? Safer from unexpected phenomena such as earthquake, such as very strong typhoon wind. Okay, that is going to be help us. If not all, is help some. The second one, okay, is compensate for the construction error. There are sometimes, especially when we construct the reinforced concrete structure like this, people subject to the weather environment. Okay, so the quality control of that kind of construction may not be that good. So factor of safety gonna taking care of that. There are some weathering, there are some corrosion, okay, in our structure. Factor of safety also taking care of it. Another one, the material itself, okay, it can have some variation. So the factor of safety will taking care of that variation. Okay, and factor of safety in the building design, you may use only 2.0. When you build some kind of aircraft, the factor of safety reduce. Ajan, why? Why? When you build the building, when you build the factory, factor of safety is 2. But when you use the aircraft, factor of safety reduce. So aircraft is more dangerous than building. In reality, like this. If you use 2.0, okay, in the aircraft design, your aircraft going to be big, very big, such as Boeing. Okay, build the aircraft that's big, that's heavy. When the aircraft like that, the aircraft will consume a lot of fuel, and it is going to be uncompetitive. Okay, to sell for the Boeing to sell the aircraft. Okay, so the Boeing must be develop very good analysis method. Okay, in order to simulate the aircraft close to the real extreme situation and use a smaller factor of safety, okay, to build the aircraft. Okay, and if the structure is important, like some infrastructure, the nuclear power plant, those kind of thing, the factor of safety can be bigger, like 3.0. Okay, so it's depend on the judgment of the engineer. Okay, your future. So we touch the design of something, connection and simple structure. The bolt, this one is in single shear. Okay, the bolt, 2 of this one is in double shear. What type of force is occur on the connection between steel and the rod? Okay, what I'm saying is we apply the force like this. Okay, and then there is going to have the resistance force here, and that's resistance force going to produce the shear occur between this one. Since there is 2 shear surface, this one and this one is going to be double shear. Okay, this one you pull the force like this. There is the ball over here. Okay, the ball over here will subjected to one surface. This is going to be the single shear. The design of simple connection. Okay, we do it to determine the dimension of the steel rod, of the plate, of the ball. Okay, we may consider the area of this. We consider the area of this. We consider the area of this. We consider the area of this. In the design, we determine the cross-sectional area of the ball. Okay, of the structural member. It may be the rod or it may be the plate. And you got to decide it to transfer the force safely without failure. Okay, such as this one. If the ball is too small during the pushing of this force F, okay, if the ball is too small, the ball will tear it. And if this one separate, okay, it's going to lose the connection. Okay, now we first come to what we should here. If the structure just like this, when you pull the structure, please be aware of what happened if the member of structure like this, when you pull it, just guess where the failure occurred, at my hands or at the middle. Marquez, if I pull this one, what do you think? In the middle. Thank you very much. Okay, so I will show you. It's in the middle. No, it's the connection between the small and the big part. But the middle is okay because the stairs here and this here is close to each other. Okay, and next, if you have a big hole like this, and then you pull, where is going to fail? It's going to fail along A, or is going to fail along along B. What is going to be along B or along A? Okay, you know that, right? Along B or along A, it's going to be this one. Why? It can be occur along this portion, and it also can be occur along this portion. Stress is going to be P over A. When this one low word, what occur is this one going to get higher. Okay, when it get higher, and then when it reach the state of the material fail. Okay, we going to prevent the failure of the structure like this. That's we do the design of the structure. So this one going to produce the stress. So the area is the main thing. It's going to be equal to P over sigma allowed. Okay, and then when you get the area, you got to check also which portion is going to be the control portion. Now we move a little bit further. The hole, I explained the hole is large. It's going to produce a failure over here. Okay, and for the shear of the section, if the connection is connected by very small bolt, okay, the failure may be for this one only two portion, may be due to the single shearing. Okay, and then there is another thing I just showed you guys before. When you pull, it may cause the failure along this portion. Okay, that is going to be the tensile failure. This is different thing. Okay, this is going to be tau equal to P over A. That's going to cause the shearing over here. Okay, the stress that's caused the failure over here is going to be P divided by the area of the plate minus the area of the hole. Okay, just compute the area. That's I just put the red line over here. Take the area of the hole out. Next, the failure may also be occur in this form. Let me put it over here. If this one is small, let me push it in somewhere else. If this one is very thin, the plate is very thin. The plate is very thin. What occur is the plate may be clutching like this. Okay, so the clutching will be occur over this small area. Okay, we will talk about kids clutching later. Or if in some case, I just show you guys about that already. If this one is not catching, but is tearing, this one is tearing. This one will produce. Actually, we use this one to compute. Okay, this one will be tau equal to P over 2A, because this one is going to be double shear. Okay, and this one also be tau equal to P. This is going to be P over 2A. Okay, and this one actually you got to compute the area of the plate in this area. I will discuss this later. Okay, so the single shear. Okay, you got to compute by doing this, and then we can he the bearing that I talking about you, this area, okay, is using to compute the stress that's called the bearing stress. Bearing stress occur the failure, produce the failure over here due to the bearing. And by doing this, we just do the stress, okay, equal to sigma over A. A is A over here. A is going to be A over here. Okay, and in the design, okay, sigma equal to P over A. And the A is going to be, this one going to be the diameter of the bowl. And this is going to be the thickness of the plate. Usually, the thickness of the plate is the one that we are looking for. So by doing this is the thickness of the plate. You have this equation to compute the thickness of the plate in the design. Okay, and then this is the bearing, the stress that occur on the plate under this one. Okay, we just have stress over here equal to P over A. A of what? A of the plate. That's we are consider. Okay, and then we put this one A equal to P over sigma bearing. This is another one of the bearing. Okay, and then the problem can be classified into analysis. That's one, find the stress. Another one, find the largest loads that occur on the structure. Okay, and then the problem is about the design. The design, you're going to determine the dimension of the structure. Now, just move into this one. We have 1 point A. 1 point A is just compute the stress. Just finish this one. Let me go further with this one. We have the steel plate AB. Okay, this is going to be the steel plate AB. Okay, it has 9 millimeter thick. Okay, and then it's connected by the 2 steel plate over here. That is going to be 6 millimeter thick. That means we combine the plate into the form like this. This one is for the AB. This is 9 millimeter thick. This one is going to be 6 millimeter thick. And then they didn't connect by the bolt. They didn't connect by the bolt, but supposed to be something like this. They connect by the screw, screwing each other for what? For 40 millimeter. They screw it up in this area. Okay, screw it up in this area. So they are going to hold it up. Pin at A is going to be 9 millimeter. Pin at C, this is big, 9 millimeter. And over here has 6 millimeter. So they ask us to find shear stress at pin A and shear stress at C. Okay, and then before we find shear stress, we got to find the shear force. And then maximum normal stress on plate ABC. And then average shear stress in epoxy. And then bearing stress occur at C. That is going to be 1 point A problem. Okay, and from the ending static, ABC is going to call to force member. So we can go a little bit further by taking this one at A only one plate. So the shear at A is going to be single shear. At C has 2 plates. Okay, it's going to be double shear. Okay, maximum normal stress compare between the green and the yellow later. So average shear stress in epoxy. Epoxy has 2 surfaces, so epoxy is going to be double shear. Okay, so we come to in this one, we draw the free body diagram. We take the moment at D. Okay, to eliminate D sub X and D sub Y. We interested in the force in the member ABC. We take the moment over here, F sub AC. And then it's going to have this distance to 40 and rotate this way. This is positive. and this is going to be in the opposite direction, the line of action here, and then the length here from here is going to be 350. So we got the force F sub AC. So we come like this. We come to the point A over here. Okay. Over here has the one plate. It's going to be something like this. This is going to be single shear. Okay. So 360,000 Newton will be the shear force over this area. That's the area. That is 9 millimeter. So the shear stress is going to be force, shear force, single shear force divided by pi r squared. This is 56 megapascal. Okay. Now next, over here, there is two force link over here. Okay, link over here. So that is what is going to be double shear. So 3,600 divided by 2 to be 1,800, and this is going to be the size of diameter 6 millimeter. The stress going to be 1,800 divided by pi r squared. So the shear stress occur at the bottom of T6 63.7 megapascal. Okay. Now for this one, there are 3 of them connected to each other, and then you got to see this screen has the thickness of 9 millimeter, and this two plates has the thickness of 12 millimeter. Consider the A. Just consider the A. Okay. The stress will occur in the smaller area. Okay. So the 9 millimeter will be controlled. But there is the factor of the bolt. Okay. This is going to be thinner. Sorry for this one. Okay. This AB is going to be thinner. Okay. And it's going to have the larger hole. Okay. This is going to be larger hole. Since this one is thinner and larger hole, so the area, the A is going to be minimum. When A is minimum, it will produce sigma max. So it's going to be produce sigma max occur in this area. Okay, so the stress is going to occur in what? In what? Sigma sub A in what? The area that's taking care is only this portion. So this is going to be the area. Okay, just take this one and this one to be this one, and then times this one. You get the largest stress, 19.05. And then epoxy produce the double shear. Okay, the force occur over here going to be the shear force, and it's going to be half of this one. So this one going to be 1,800 Newton. Okay, and then it's going to divide it by the area 30 millimeter times 40 millimeter. This is the area of the epoxy. So the stress is only 1.5. It's a glue. Okay, so the bearing stress will occur on the area. Okay, at the C over these two areas. So force divided by half, and the area going to be this area, 6 millimeter by 6 millimeter. So bearing stress is going to be 50 megapascal. Now I choose finish my lecture over here. Okay, that's the end of my lecture. I will talking about 1.B later. We have this one already. You just follow this one, and then we have the example of the design for the next lecture. Okay, I like you guys to go through all of this one. I will come back with analysis 1.b and the design. Okay,